Okay, shall we start? と、So, Zafira-san, I sent you a document about beam with viscoelastic damper. It is a little bit complicated. Well, can you see my document?
Yes.
No? So the point is, we have a shear spring with viscoelastic damper. So it is a velocity dependent, right? But usually force deformation is force and deformation. So this velocity, how to say, well, we must establish incremental form step by step by computer. So I will go back to the final one. So let's see. なんていうのかな。well, actually, before step 1, maybe this is step 2. So nodal deformation, delta theta, is obtained from, well, for example, Newmark beta method or time integration method. Okay? Then we use this formula to get the increment of damper displacement. Calculate. This is a eta is a damper displacement. Okay? And then we must calculate well, another displacement. Actually, there are 3 types of displacement. One is elastic element and nonlinear bending spring. So the first part is elastic spring. Second part is a nonlinear spring displacement deformation, and the last one is a shear. Okay? So now we obtain this shear deformation, and so in step 2, step 3, we calculate the elastic deformation increment and the nonlinear deformation increment. Okay? And if we know nonlinear deformation, we use hysteresis model to get the force increment, right? And finally, we will get the nodal force. Get the nodal force. And the nodal force is used for time integration method. So we go back to step 1, next step. So this is a process. And I almost finished writing Stella 3D source code. I'm checking how it works.
Thank you so much.
I hope this theory is correct. Maybe this weekend I will finish and I will send you.
ありがとうございます。
Yeah, well, it's interesting, but not so easy.
Yes.
Sensei, I have one question.
Yeah.
I was checking the formulation,
Yeah.
and in equation number 7.
Number 7.
Yes.
Okay. Yeah.
Sensei, here the rotational displacement is found from the shear displacement. So will it not be 1 by L into eta?
So, yeah. Well, could you repeat again what your question?
My question is that here the rotation is found in eta A and eta B
Yeah,
from the shear displacement of eta.
yeah.
So to convert the shear displacement into rotation, should it not be 1 by L into eta, like 1 by L and 1 by L?
Yeah, you are correct. Yes. So it should be yes. そうか。Yeah, you are correct. So, well, we can write here. No, maybe. So eta is angle, actually. And this viscoelastic damper, this velocity and deformation is a shear deformation. So I must divide by length. Or we must multiply L.
Yes, sir. Yes.
And maybe this is better. Okay, thank you. Yeah.
Yes.
Yeah. Okay. So it means, let's see, this part will be multiply. Velocity. It is. This is wind L. Maybe. Sorry. This is okay. This is okay. This is fine.なんか違うよね。Okay. I will check again. Thank you.
I think it is correct now. It will just multiply.
Yeah. Okay. Thank you. Yeah. So, Zakura-san, could you show me your Excel file? You calculated K and S of...
Yes. Can you see my screen, Sensei?
Yeah.
So this is C and this is C.
Okay.
Yes, so I choose material type from C, and then this is 0.9 for GE, and GC is this one times, divide by particular frequency because we only want GC. So this is the formula. And then after that, we adjust we have to determine the area for the shear area, and this is total shear area. And then from here, we can get the total layer by this one is the area for one slice of viscoelastic material, and this is the thickness, and then we can get K and C.
One moment.
Okay.
I want to check one by one. No. Okay. Could you click GC again?
GC?
Yeah. So, okay, 0.17 is GC multiply omega.
Yes, sensei.
Multiply omega. So, if we want to calculate GC, you must divide by omega.
Yes, sensei.
And omega is 2 pi
F.
And F is 3.5 hertz.
Yes, sensei.
Okay, yeah. Okay. That looks good.
Okay.
And height with this is 85 centimeter with 20 centimeter. Oh, it's a very big damper size.
This one 4.5 cm. Sorry, 450 mm times by 300 mm. Is it?
Why height is 850 here?
Which one? This one.
Actually, this one we can control
to get the capacity. For example, this capacity is around 800.
No, I'm asking height. Height is 850 millimeter.
No, like if you see from here, this is the one slice of viscoelastic. This is total area. Mean the total in viscoelastic.
But what is the meaning of height and width here?
I just want to get area, the total area, so I can reimagine if this is the total area.
Which one is height? 450 or 850? Which one is the height?
The height. It's like this, sensei. In viscoelastic, imagine that we have many layers, right?
Yeah.
So these many layers we can combine into one sheet, one big sheet. So it doesn't matter width and height because we're going to cut it into small pieces, which is this one, 450 times 300 mm.
So what is the meaning of this number, 450?
It's the size of the small viscoelastic that we sandwich with metal plate.
And what is the 850 and the 800 here?
I want to get the total area here, sensei. The total area of the shear area. We know that viscoelastic.
Sorry, I don't understand.
Viscoelastic damper, sensei. It is a page based on the shear area.
Could you write a picture?
Picture?
Yeah, figure.
Okay.
I cannot understand.
It's okay, sensei. Okay. Maybe I should print. Okay. Can you see my screen, sensei? So, for example, in viscoelastic damper, we have many layers. Example. So this is a steel plate, and in between have viscoelastic material.
Okay.
So in the formula is K, for example, K equal to GE times area, the shear area, divided by H thickness. So we have to determine the total area of shear area. But if we see viscoelastic is like a beam shape. Okay, I show you this one. So viscoelastic here. It doesn't have. In the middle, we have the viscoelastic material like this. So from one in the calculation, we calculate in the big, like the total area, the big size, and then we can cut it into small pieces and put sandwich in between the plates.
Yeah.
So that's why first I calculate the total area.
So this is a big area.
Yes, sensei.
And then you cut it into small pieces. Why you do like this?
Because viscoelastic is like sandwich type viscoelastic material with metal plate, right, sensei? The contact between the viscoelastic.
What is the size of 850? Why did you adapt this size?
850.
Yeah.
The main purpose is I want to get the total area, AS. AS is here, if you can see the formula. So,
yeah. Total area with multiply height, right?
Yeah, this is the small area. This one, 450 times 300. Okay, this is AS, sensei. This is AS, the total shear area. Okay. But this side is very big. So
850 is size of this.
Yes, 850 and 800. But this size is very big. So we want to adapt to coupling damper size, right, sensei? So we can cut this and sandwich with the metal plate. The small area. So here we get 5 layers.
So area is now small area.
Small area, but when we sandwich with the metal plate, it sum up together. Total.
And what is the meaning of H?
H.
H, yeah.
H is the thickness.
Thickness of one layer or
One layer. This is H. Yeah. That is what the meaning of this.
So where did you use this 450 and 300? Where did you use?
And 300 here. This is steel plate.
But in your Excel file, where did you use?
Where I use
150 and 300. Where?
I divide the total area divided by this area. So I get how many layers that I can put in the viscoelastic.
Could you click K?
Okay.
Yeah. So if you J3 multiply Q3, O3, divided by H. So how did you decide H?
H.
If you want to increase the capacity, we can adjust the H. For example, if I put this is 5 mm, the capacity will increase. So my
thickness is increased.
Yes, my target here from the Sierra 3D. This is the beam model that we did last time. So if we get from the beam here, 1, 2, 4, times by 2 divided by 300 centimeter, we get 827 kilonewton. So if I put, I want a capacity around this 800, so I put 9 mm thickness.
So what is the meaning of 5 layer?
Five.
How to say? Could you go back to Excel file? I think it's better to put this part is 450 because size of damper is 450 and 300, right?
Okay.
And the area is multiplied this two value.
Okay.
And layer not necessary. And H is how to say thickness of this.
The total thickness.
Total thickness, yeah.
Okay.
And is there any, how to say, you change H, but I don't know the product of viscoelastic damper. How much thickness? I mean, you can commercial.
It depends on manufacturer, but usually it's like 5 or 5, 10, 15, and 20, like 5 mm difference.
So you can control layer, but maybe you cannot control thickness. It is fixed by the manufacturer.
But another thing that we can do if we want to, for example, the thickness that we say is 10 mm, we can change the area sensing. So So it's either way around.
But the area is also, if you decide a beam size, you must fix the area. You cannot change. So only you can change is the layer.
Yes.
How many layer you put. Right? So area is 450 and 300. It's fixed.
Okay.
But and the H is also fixed. You can change layer.
Okay, sensei.
In actual design, I think.
Yes, understand.
And please find out how much thickness of one layer.
Right. Okay.
And I also don't know what is standard thickness of the viscoelastic damper?
I think Nippon still have the catalog for it because most of the paper that discuss about viscoelastic city and they apply the damper to the real structure building actually is from Nippon Steel. So I will find. Yeah.
But you don't know if they have catalog or not.
I will find.
But are you sure you can find?
If not, would be like this.
It's a catalog.
This is
okay.
This is but this is different type of viscoelastic damper. This only have one layer.
Is this for earthquake shaking or what purpose of this?
It's for German university.
No. What is a earthquake or what vibration they want?
Maybe vibration. Maybe I can find it later.
Okay.
Yeah. So and I also recalculate about the how we combine viscoelastic and metallic and also the support. So this is for metallic damper and this the couple wall stiffness, and from here I use this book sensei from here, and then this is viscoelastic only, and this is combined with support in this book, but here the support I changed to metallic damper. So but the formula I can use same as this one. It's just change the stiffness. So here we have viscoelastic.
But in this case, KB is elastic stiffness.
Elastic stiffness, yes.
So it's not the hysteresis damper.
Okay, I understand. So this stiffness should be two. One is elastic, another one is plastic.
No. So it's not so simple.
Yes, it's not simple.
Yeah.
So the metallic, when we combine metallic, it should be combined like this and like this. But since this one is not constant, it's inclined. So it's okay because last time we discussed that after elastic it's almost constant.
What do you mean constant? What do you mean?
The force is constant.
Force is constant.
Until one point and it turns back.
So you mean the force is constant means flat?
Yes.
After yielding?
Yes. It should be like that.
But how did you get this figure?
This one? By calculation from this.
And how did you decide second slope, this stiffness?
Based on this experimental data, sensei.
And which factor is related to this?
This one. So the second stiffness is
Second stiffness. What this? What is meaning? What is this? Would you magnify?
Can you see sensei? KDS. The stiffness.
How did you decide the second stiffness?
Based on this, actually this is a test with the metallic damper, and then I try to get how much the second slope from the
do you have a picture of test result of other damper? Is it similar to this hysteresis?
This is what I get from the...
So it's almost zero stiffness after yielding. But why you have a second slope?
In the one that I calculated, they have like second stiffness, like second slope, not totally zero.
Why?
I'm not sure.
Why?
Let me see. Sensei, can I find the paper and give back to you later? I forgot where it's. And then this one I cannot use, sensei. This formula.
Yeah, but because this spring is, if this spring is nonlinear, you cannot increase force. There must be a yielding force, right?
Yes.
But if this is a linear spring, elastic spring. That's why your hysteresis is increasing.
This one, sensei. Actually, viscoelastic, I separated. The blue color is viscoelastic, and then the orange viscoelastic plus metallic, and the gray color is viscoelastic, metallic, and also support.
Yeah, but in any case, it can be increased a lot. No limit.
I see.
Where the metallic damper yielding? Your model, this equation cannot simulate nonlinear metallic.
Okay, sensei. I understand. I'll be finding again to correct this exam. Sensei.
Okay. Yeah. Sarah-san, do you have anything you can show me today?
Yes, I have. Today I'm going to talk about historic graph of the viscoelastic damper. And first of all, about general structure of viscoelastic dampers, and Viscoelastic damper utilize multiple layers of a solid viscoelastic material sandwiched between the multiple steel plates. These dampers activated by interstory shear and deformations, and for example, a brace or wall panel design. And then for about energy version in the viscoelastic dampers, when the lateral load acts on the structure, wall 1 deflect and create moment bottom of the wall, and then the force from wall 1 transfers to the coupling beam where the viscoelastic damper are located in. And the viscoelastic damper dissipate the energy from the friction between the viscoelastic material and the steel plate. This line is a friction, and this convert the kinematic energy into the heat energy, and so contact shear area is important consideration viscoelastic damper in this design. This presentation's main point is the viscoelastic force formula. This viscoelastic force is depend on the time, and K is stiffness, C is the viscous, this K, X is the target displacement amplitude, and this omega is circular forcing frequency. This and have to find the stiffness and the viscous. Stiffness equal to the shear storage modulus is multiply the total shear area divided by the thickness of the viscoelastic layer, all layers thickness, and viscous equal to the shear loss modulus is multiply the total shear area divided by the thickness of viscoelastic layers. In this data, we can see the material type and the shear storage models and the shear loss models. And how to find the target damper capacity. In this stereo 3D, I built the 10 stories with the coupling beam with the steel, and this moment is this data I got from the data beam of the coupling beam with the steel, and from this moment I got this capacity in here, 826 same kilonewton. This is the max capacity, right? And I choose this material type. I got the C, and shear storage model is 0.19. From this we find this shear loss model, and height and the width is 1.5 meter, and width is 1.5 meter. From this we find this total shear area in here. Viscoelastic layer area is 320 millimeter and 520 millimeter, 330 millimeter. And from this we H is the thickness of the one layer viscoelastic layer. It was the 5 millimeter, and we can find this from from the layers necessary layers in the damper. And before I show this formula, from this formula, find this. Okay, and after that, without coupling beam, we got period 0.655 seconds. From this, we find the omega circle frequency and 9.593 it was. From this, in this graph, it describes the inclined ellipse as shown in here. It depends on the force and displacement. And blue one is a design 100. And when the capacity decreases, the force also decreases. And before I show indicated by the max capacity in here. This blue one's the max capacity was in here.
Okay, so you try to design damper.
Yes.
And the damping force must be less than the capacity of the beam. But how did you decide this 9? This is a centimeter?
This one is?
Yeah.
This is millimeter.
Why did you adopt 9?
And this is random number.
Random number, but if you increase this number, what will happen?
Increase the number?
Yeah. Could you put another number here?
To the matter.
Yeah. So the force is increasing.
Yes.
So this force will be larger than the capacity of the beam.
Yes.
So how do you control this?
If the displacement is larger, how to control?
Sensei, can we use the initial displacement same as the target displacement of the building?
Target displacement of the building. Maybe, but we don't know. I mean, real displacement. It depends on the earthquake. So for example, if we assume 9 millimeter for deformation, I mean target deformation 9 millimeter, but the real deformation will be larger.
Yes. Actually in real, I think Sarah, you put this one based on the test displacement. The test displacement is very small. But if we check the paper which applied to real building, usually displacement around 50 mm to 60 mm. Yeah. And Sensei, I found one catalog describe about the viscoelastic. Can I show the screen?
Okay.
Can I stop sharing?
Thank you, Sarah.
Here is one company that have catalog for viscoelastic. So this is wall type. One is wall type, another one is like bracing type. So this is the size. So basically the standard and it also state the maximum displacement here. And here it has size. And also it's described thickness 5 mm, 10 mm, 15 mm.
Yeah, actually the size of viscoelastic material is here. And this is the total size of the device.
Okay.
So this is a 5 millimeter rubber inside 47 millimeter, increasing this outer steel plate. Yeah, so this is the size of wall size, 800, and the height is 100 centimeter, and and inside this is a 5 meter rubber. Could you go down? Okay. And the area is 0.4 square meter. Okay. Yeah. So we can assume one layer of 5 millimeter.
Okay, thank you.
And if you 10, 15, so 2 layer, 3 layer, something like this. Well, I don't know. They can control thickness as you want. So in your case, you said area is 450?
450 times 300.
Right? So this is the area of rubber.
Yes.
Viscoelastic rubber. And the thickness, you can assume, I don't know, just one layer, it should be, for example, I don't know, 10 millimeter, one layer. So you can put 2 layer or 3 layer, depending on how much damper and how much capacity you want.
Okay.
Well, I don't know. If they manufacture 30 millimeter thickness, only one layer, it is also possible. But from this table, it looks minimum layer is 5 millimeter.
Yes.
How about the paper of, how about the device you found in the book?
Device is a small test.
Because this is a wall type damper.
Yes.
Our device is not wall type.
In the Christopolis.
Yeah.
This is actually a test.
But it's a real size test.
It's a small
size?
Small size.
Really?
Why is it have?
But they already adapt for high-rise building.
Graphite. I have to reopen. I believe the big one actually is found in paper, but they just use the properties in from Christopolis. In Christopolis, they use a small device because if we check the displacement of the H-series is also very small and the force also very small. here. So we start from here. So this is the picture that they give.
Oh, okay.
It is very small.
But there is another paper
Yes.
writing about the device in the high-rise building.
Yes. Okay. This one.
And then, well, yeah, it looks real size test.
Yes.
People is here, right? It's very big size.
Yes.
How much size of this?
This damper. I think my PDF doesn't work.
Okay, please check.
Okay, sensei.
And which company? You found the catalog. Which company?
This one. Actually, my Jima-san sent it to me. So.
住友理工です。
あ、住友理工。
はい。あと新日鉄も同じようなやつがありました。
住友理工は、うちの学生、あれ、ファイサルだっけ小牧にある住友理工に働いてるから、じゃあ、OK、聞いてみようか。We can contact 住友理工。
はい。
Yeah, maybe we can visit this company. It's not so far from here. Architecture.
Okay, sensei.
Komaki City. And there's a student who is now working for this company. I hope he's still there. He's from Bangladesh.
I see. Okay, sensei.
住友理工ね。Okay. Yeah, so if we can, how to say, I don't know, maybe we can do some joint research to do some experiment if they are interested in. Okay, so let's see. Ataya-san, you are the next.
I read this paper, the total mass distribution of multiple mass samples for vibration control of structure. And they have modeled the main system as a land mass, only 1 degree. And here the past many dampers. And they presented this formula to point the angular frequency of each damper. With omega here is the total and the average. And this is the region. It means the range of frequency from CMD1 up to CMDN.
Okay.
So they said that this black line is when all, for example, if you attach 11 CMD to the attack. For example, and the structure has 2% damping. Total mass ratio is about 1%. So the black line is the response curve of the main structure with the vertical axis is dynamic magnification factor and the horizontal axis is frequency ratio. Omega is frequency of excitation, harmonic excitation, and omega is angular frequency of the main system. So they said that the main approach of the study is to transform the peak regions to a very smooth and flattened area and decrease the dynamic magnetism.
What is the meaning of black line and the red line?
Red line is just oil draw. They want to transform this black line to the red line almost. It means that
Black line is also fluctuating.
yes, it is just an example. Maybe in the next slide you can see. But this black line is when the element PMDs all have the same mass. Okay? But they are going to, for example, change the amount of PMD mass to flatten this curve, the response of the main system.
Okay.
They said that there are two mass distribution methods, but one of them is probabilistic mass distribution, and another is bell-shaped mass distribution. Here, you see that L1 PMD, for example, the number 6 has the most, the biggest amount of mass, but others are smaller amount has smaller amount of mass. In the bell-shaped mass distribution, there is almost half of them, about 6 of them has almost the same mass, but others has smaller amount of mass.
Okay.
We presented just this equation just for this model, their own model. It's not a closed form for every theory. So, n is the number of PMD, one is just only the degree freedom of the main system. And A can be any positive number that it just dedicates amount of mass to other PMDs that you can see later. So they want to just focus on this two method of mass distribution. First, they just keep the constant value of A, mass ratio, damping, and number of dampers, and only play with just the bandwidth of frequency. This is how to say the distance of each PMD frequency. So they played with many numbers and finally found out that if the beta is about 0.15, the response curve will be very flat, and the peak will come down, and the alley will go up. So the best or the optimum value for beta is 0.15. So when they found this value for beta, which is optimum, they will play for damping of PMD. Many numbers, and finally found that 18%, no, 1.8% is the optimum value for PMD damping. That makes the response curve very flat in the middle and bring the peak values lower. And finally, they search for the optimum A that we saw in the formula. So in that case, we can see that the response curve becomes more flattened in in this area, and values are come down. It means that the dynamic magnification factor decreases by changing the mass of each TMD, you can say. And also they just modified that formula again and it used parabolic mass distribution. It means that maybe I can show a in here, for example, since this formula is a parabolic, in this area TMD has more mass, but in this part TMD has small mass. If you change the value of A, for example, become smaller, it's more difference between mass of TMD is very small. But if that value goes up, the difference also becomes increased. So in this modified formula, the gamma is the ratio of each TMD frequency to frequency of main system to exponential of R can be any number, positive or negative. If it is positive, the right side comes down and the left side goes up. But if it is minus, the opposite case will happen. So in this case, because they state that in here, this point is a little higher from this peak values, so we can make it more equal, this peak and this peak. So they modified this formula. And this formula is for the bell-shaped mass distribution. But finally, we can see that dynamic magnification factor as a response curve. It's very flat in the middle. As since the foil that you prepared for advanced structures, there is a two peak. Those two peaks are equal when parameters are optimum. But here they decrease these two values more than those by installing many TMDs. And finally, from this, I found that, for example, my 20-story building, the first mode has about 5 the angular frequency, and the second mode is 12, and the third mode is 19. When the building starts yielding or collapse, for example, close to become collapse, the frequency becomes smaller. So this TMD will not work. If we can design another TMD that its frequency is smaller than fundamental frequency of the structure, maybe it will work after yielding of the building, because in this case we just widen the range of frequency. And that's also true.
So you think putting many TMD is effective even main structure will enter nonlinear?
No sense not increasing the number, but one or two other TMDs, their frequencies are smaller than the first mode of the structure, because they help the building after yielding, because after yielding the stiffness of the building decreases. When the stiffness of the building decreases, it means that the frequency also increases. So there have to be another TMD 2 or 1 to work when the building goes to yielding.
So what is your suggestion?
Since it needs a little more searching that after yielding, for example, how much the percentage of stiffness decreasing, how much will be. In that case, we can choose a frequency for that, and can design a TMD after yielding.
Okay, so I mean, why you introduced this paper today?
At first, it was I thought maybe it is for seismic loading, but it was just for harmonic excitation. But the range of frequency was somehow a new idea that maybe we can consider the optimum range of frequency for TMD.
Yeah. So yeah, it's a good idea to put multiple TMD. One is for elastic range, another one is for tuned for inelastic range or something like this.
Yes, but the model has to be frame model, not landmass model. And also, since I was rating if you have checked why the landmass don't work on the wind load.
Taya-san, actually, it's not easy. I tried, but it's not easy.
Okay.
Yeah, because there are many reasons. For example, in lumped mass model, you have a lumped mass and 2MD is connected by rigid floor.
Yes.
And when you apply wind, we want to apply wind only for main building.
Yes.
Not TMD.
Yes.
Right? But it's not so easy. But if you put the TMD in a frame, and you can, how to say, apply the wind only floor level of main building. So TMD, there's no, wind force on TMD. So in case of Saranya-san's case, it's okay. But in your case, it's not easy. I gave up, actually.
Okay.
So I think it's also a good idea to discuss about TMD after yielding of the building.
Yes, it may be at least we can work just only with single TMD.
So even your lumped mass model, and you connect to one TMD, another TMD, another, so you can put multiple TMD on same floor. Right?
Yes, there was another paper that said that they were discussing the serious attaching of multiple TMD. It means that the second TMD has to be attached to the first TMD and so on. But I'm not sure that that serious attaching will lead to a good result.
And also, it's worth to discuss about. I remember you said TMD first mode is around top, and the TMD for second mode is anyway close to top of the building, right?
Yes.
And first mode, first frequency, it will change after yielding.
Yes.
But the second mode actually not so affected by yielding.
Okay, Sensei.
Yeah.
It means the first mode frequency will decrease, Sensei.
Yeah.
In that case, the TMD will not work. If we have another TMD which is tuned to a smaller frequency, maybe after yielding, that TMD will work.
Yeah, so maybe you can put the 2 TMD for first mode elastic, first mode not inelastic.
Yes, Sensei. But it needs frame model, I think.
Yeah, so also another idea is to you extend your model to be frame. But it takes time to calculate response, so frame model should be very simple. I don't know, most simple is 3 by 3. 3 by 3, and you put the center part as a TMD you arrange.
Yes, Sensei.
Please discuss with Saraya-san how to do it. Yeah.
Thank you.
Good, very good. Okay. So, who is next? 誰か他に発表する人、真島君は？
僕はないです。
ない？ Okay, so shall we discuss next meeting? So after I success for the model of viscoelastic, and also we check the effectiveness of the viscoelastic damper for coupling beam, then we contact Sumitomo Riko company, and maybe we can do online meeting together first. Okay, so today is 16. 佐藤工業の来週はちょっと忙しいですね。So next week I'm a little bit busy. 1 o'clock, 4 o'clock, 21. How about 26? I don't know.
Okay, Sensei.
10 o'clock in the morning or 3 o'clock afternoon? Which one you prefer?
3 o'clock in the afternoon.
3 o'clock afternoon?
Sensei, I am actually going to Tokyo that time.
When you come back?
I come back on 27th evening.
Okay. How about 28 or 29?
28, Sensei.
28. Okay, so 28, 3 o'clock. Okay? Is everyone okay? Yeah, okay. And Mr. Hao from China will come 28. But Gao-san will take care. So maybe I am okay. Okay, so that's all. So see you at the barbecue. Okay? Yeah. Bye-bye.
Bye, Sensei.
Only the one by one. The reason is that the shared deformation will be half. So for one direction, it will be eta by 2 by L by 2. So by 2 will be.
But the L loss is not the length of the beam. And when you have each end, you have L over 2, L over 2.
Yes, but like we have L by 2, L by 2, but the whole deformation is also by 2.
Yeah, but that deformation is in each end.
in each end. Yeah.
So you divide by 2. Because you have NA and B equal N. No, eta, no?
Eta.
Eta. Eta A, eta B equal eta, and that eta should be divided by 2, no? Because it's for eta A and eta B.
No, like eta is the total deformation. Like
eta is the total deformation.
Yeah, eta is the total.
Oh.
In the technical manual also I found this, that it is 1 by L.
In the technical manual,
Yeah, in the technical manual if you go to page 112.
112.